We've already started to touch on the usefulness of submicroscopic thinking for dealing with chemical problems. Thinking on the molecular level is a fantastic way to proceed with problem solving in chemistry and think really rationally about how chemical substances behave. In this video, we're really going to solidify what we mean by submicroscopic models and the submicroscopic level or realm of thinking in chemistry. We'll also look at the other two realms of chemistry, and these three sort of realms or ways of thinking form a construct known as Johnstone's triangle, which is highly useful for thinking about chemistry in very general terms. And then we'll zero in on the submicroscopic domain, which in my eyes is one of the most underappreciated of the three, especially among students. It's very easy to get by without submicroscopic thinking, but thinking this way will make your life so much easier, particularly in introductory chemistry, where you'll see chemicals in a wide variety of contexts, but a unifying theme throughout all of it is thinking about what's happening at the submicroscopic or molecular level will help you get the right idea of the general behavior of chemical substances. And so we're going to focus in particular in this video on submicroscopic models of molecular compounds and ionic compounds, the differences between those and the similarities between those, and also the role of phase or state of matter in how we think about the submicroscopic level. Before we get there, though, let's talk about the three realms of thought or levels of thinking in chemistry. These three form a triangle. At the 3 points of the triangle, we have the three domains, is another word you'll see used, of chemical thinking: the macroscopic, symbolic, and submicroscopic domains. And there are little cartoons here that give us a sense of the kinds of imagery and text and things that we see when thinking in these different realms or domains. We have a macroscopic explosion, for example, in the course of a very vigorous chemical reaction between hydrogen and oxygen gas. We have a symbolic representation of that reaction with chemical formulas for the reacting substances and the resulting substance at the end of the reaction. And then we see balls and sticks in the submicroscopic representation, and this is an actual physical representation of what the atoms and bonds in the reacting molecules and the final product molecules actually look like. And these three realms are interrelated, and this is a key point of the triangle, that we move between the domains regularly. Maybe we start with macroscopic observations, and from those we develop a symbolic model of what's going on. Maybe from a wide variety of macroscopic observations, we develop a submicroscopic picture. Maybe the submicroscopic picture gives us insight into the macroscopic situation if we notice, hey, I've seen these balls and sticks doing something very similar before. We move between these representations on a regular basis to connect different types of knowledge and, in many cases, gain deep insight into what's going on, especially at the macroscopic level. If we just were to stay at this sort of surface level, in a way, right, we'd be stuck in the 1800s. We'd be stuck at a time when we couldn't really think submicroscopically or symbolically. We weren't sure, for example, that matter was made of atoms. So atomistic thinking on the submicroscopic level would not even be something that would cross our minds necessarily. So we'll talk about the three domains in detail. Definitions for the three domains are at the top of this slide, but we'll zero in on their details in the ensuing slides. And the key thing to keep in mind with this graphic is that these domains or realms of thought in chemistry are interrelated. The macroscopic level is the first thing we'll touch on, and this is the bulk, quote-unquote, level. You might have seen the word bulk or in bulk on the previous slide. These are direct observations of chemical properties and reactions that we can make with our five senses: eyes, ears, etc. So things like color, odor, the amount of stuff sitting in front of us if it's macroscopically visible. These are all macroscopic properties, and measured properties like mass, amount in moles, temperature, volume, pressure of a gas. We can only make these measurements on macroscopic samples in general, and so the properties will arise from the macroscopic level. This actually has some profound implications. The properties that we measure are sort of statistical. We won't get into the details of this at all, but one thing to appreciate about the macroscopic level and its connection to the submicroscopic is that there are an unfathomably huge number of submicroscopic particles or formula units in a macroscopically visible sample of absolutely any substance. So statistical effects are really, really important at the macroscopic level. You'll start to develop a sense for this when you get into discussions of the second law of thermodynamics and the way it governs chemical properties and reactions. Intensive bulk properties like density, molar mass, melting point, boiling point, again, things we can measure for a substance on a macroscopic level that maybe don't depend on the amount that's there. This is what we mean by intensive. These are still associated with the macroscopic level. The bottom of this slide, I've got three representations, we might say, of this chemical compound: 2-methyl, 2,4-methylpent-3-ene-1-il chromane 4-one. That is an absolute mouthful. On the left, at the macroscopic level, we have just a photograph of the substance. It's a yellowish liquid at the macroscopic level. The color, the fact that it's a liquid at room temperature, the viscosity of this liquid, the mass, the volume, these are all macroscopic properties. At the submicroscopic level, we're looking at a single substance-defining particle of this substance. This is not directly observable in 99% of cases. We generally cannot see atoms and bonds, and so what we know about the submicroscopic level comes from hypotheses, theories, and models derived from experiments. Typically at the submicroscopic level, we're striving for as much physical accuracy as possible, as much physical accuracy as the human mind can comprehend, generally, in looking at, for example, a molecule as large as this. So we often represent bonds as sticks and atoms as spheres, and maybe the distance between the atoms tries to model the actual lengths of bonds in the actual substance. The way atoms are connected reflects what we know about how atoms are connected from experimental evidence, things like this. And so there's not a lot missing here. We're striving for physical accuracy as much as possible in this representation. You'll see even more detailed submicroscopic representations that look at, for example, electron density, where electrons are located in a molecule like this. That starts to get a little visually busy, but that is part of the submicroscopic level. Anything that happens on the single molecule scale or single formula unit, or even a few formula units, maybe up to 20-ish or so, this is all the submicroscopic level. And at the submicroscopic level, we'll see the interactions between atoms within the molecule, chemical bonds, right? We also might see interactions between small numbers of molecules, and we're going to return to this at the end of the video when we look at the lingering questions here. The last level or domain of thinking in chemistry is the symbolic level, and this word representation is really key to the symbolic level. The symbolic way of thinking when it comes to chemistry is all about representing either the macroscopic or submicroscopic domain using a human-friendly representation is often the term I use. The goal is often to communicate information with other human beings efficiently and effectively, and sometimes this comes at the expense of physical accuracy or relies on conventions that the community of chemists understands to be the way we talk to each other. So, for example, on the right here, you're seeing actually two symbolic representations of this chromane 4-one compound. The chemical formula in and of itself is a symbolic representation that gives us information about the numbers and types of atoms in the compound. And this skeletal or line angle drawing that you're seeing above gives us information about how the atoms are connected. There's a lot missing here if you compare this to the submicroscopic representation. There are no hydrogen atoms drawn. There are no letter C's for the carbon atoms. Instead, we're seeing the convention that carbon atoms are sitting where bonds intersect with each other. So there's a lot of information compression that happens, and this is common at the symbolic level. Part of learning chemistry is learning these conventions and the way information is compressed in chemical representations. What you'll often need to do in solving problems, for example, is sort of decompress that information from the symbolic to the submicroscopic level, for instance, recognizing where hydrogen atoms are located from this compressed symbolic representation. For example, not something the details of which you need to worry about right now at all, but this is absolutely something you'll start to do as you advance in your chemical education. 3 general classes of compounds that you'll encounter in chemistry are shown on this slide, and we distinguish between these types of compounds based on differences in the way they look at the submicroscopic level. Molecular compounds are composed of discrete molecules with a good bit of empty space between the molecules, and this substance on the left here above the letter A is benzene, and what you're seeing is a collection of benzene molecules arranged in a regular lattice, but with a definite discrete molecular representation or situation at the submicroscopic level here. There's a lot of empty space between adjacent benzene molecules, and we can see the carbon and hydrogen atoms in these molecules are not really connected to anything else aside from what's inside this one functional unit. Small numbers of atoms bonded together with relatively large distances between the discrete molecules. Ionic compounds, as I believe we've already seen, contain an infinite lattice of positive and negatively charged cations, so it's not really possible to isolate a single molecule in here, right? Where is the molecule of NaCl in this lattice, right? Is it here? Is it here? Here? Essentially, it's everywhere, right? And because ionic bonding is sort of omnidirectional, there are not discrete molecules within this substance. It's an infinite lattice of positive and negatively charged ions. Covalent bonds can also extend out over very, very, very large distances and involve very, very large numbers of atoms. And in that case, we're looking at something that has covalent bonding, but resembles an ionic solid in having an almost, or sometimes de facto, right, a practically infinite lattice of bonds and infinite lattice of atoms. And when those bonds are covalent, this is called a network covalent solid. This is a representation of graphite on the right of the slide. Diamond is similarly a network covalent solid. And for example, a sheet of graphite, which is known as graphene, you can think of as one massive covalently bonded molecule, if you like, or you can think of it as a network covalent solid. In diamond, instead of flat sheets, we actually have a 3-dimensional network of carbon atoms all covalently bonded together. Whenever I see a diamond, I always think about this fact that it's actually, you're looking in some sense at one molecule, right? Since all of the carbon atoms are covalently bonded to each other in a diamond. As chemists, we're frequently concerned with the 3 states of matter: gas, liquid, and solid. Gas is known as a dispersed phase, and the solids and liquids are collectively known as condensed states, since particles are relatively close to each other. And I'm actually going to start with the submicroscopic representations of these states of matter, because these should really be burned into your memory before your first chemistry class. In solids, the particles are very close to one another. Things aren't moving very much. There might be a little bit of vibration in place, but really the atoms or molecules are stuck to their positions in a solid. In a liquid, particles remain relatively close to one another, but now they can sort of flow freely over one another, and this is why liquids flow at the macroscopic level. The particles can freely move past one another, so they're still stuck together, just not as tightly as in a solid. And in a gas, well, the particles aren't stuck together at all. There's very large distance between adjacent particles. The particles are in motion, bouncing around their containers, and in a sense don't really interact with each other at all. So gases expand freely to fill the volume of their containers as their particles continue to move until they hit a wall, at which point they bounce off and still continue in motion. And so these submicroscopic representations of gases, liquids, and solids give rise to the properties that you see indicated above. Solids hold their volume since the particles are sort of stuck in place. Liquids are able to flow since particles can move over one another. And gases expand to fill the volume of their containers, and particles within a gas don't really interact with one another. Keep these representations in mind. They'll be highly useful, especially bridging the gap from the macroscopic to the submicroscopic. macroscopic perception of a solid should immediately clue you into a molecular representation that looks like this, for example. Symbolically, we represent the states of matter using what are called phase designators or phase indicators. A phase indicator or designator is listed after a chemical formula in parentheses. And again, just like observing at the macroscopic level that a substance is a solid, a liquid, or a gas, a phase designator is a symbolic way for us to get the correct submicroscopic model from looking at a symbolic representation, right? So solids are represented with the letter S, typically italicized inside the parentheses. Pure liquids with the letter L, and we often use this kind of cursive L to distinguish the L from the number 1, for example, or just a smudge on the page if you're writing. And gases are denoted with the letter G. So just to back up to the previous slide, we would be able to go from, for example, seeing this S in parentheses in a chemical equation or after a chemical formula to this submicroscopic model. A cursive L in parentheses would give us this submicroscopic model, and a cursive G in parentheses points me to this way of thinking about that substance. And so, for instance, just to back up one more slide, seeing this tells me that symbolically it's always going to be okay to list an L in parentheses after the chemical formula, and this gets me to a perception of how multiple molecules that look like this exist within this liquid at the macroscopic level. When we take a substance and dissolve it in a solvent to form a solution, which we'll touch on more in Module 3, the substance has very different properties in the solution phase than it does, for example, in the solid or liquid phase in many cases. And so we use this aqueous or AQ phase designator to represent a substance dissolved in water in particular as the solvent. So for example, when we take sodium chloride, which has the chemical formula Na for sodium, Cl for chlorine, Na plus Cl minus, right, sodium chloride. When we take that and dissolve it in water, in fact, things look very different on the submicroscopic level than the solid ionic lattice we're now used to for solid sodium chloride. We're going to hold off on looking at that submicroscopic picture just for the moment, but we'll eventually connect this phase designator for the way a substance looks when it's dissolved in water. And one thing to note about this, and this gets at the second bullet point on the slide, is that the NaCl in the solid phase, when it's a pure substance and sitting there, table salt in a shaker on your dinner table, is a very different thing than sodium chloride that has been dissolved in water. And so we use different phase designators to emphasize the difference between this substance in one phase versus another. And as I mentioned, we'll return to solutions in more detail in Module 3 and connect this AQ phase designator with a submicroscopic picture of solutions. Our lingering questions from this video, the first is about mixtures. Just mentioned this. What's going on with submicroscopic models of mixtures, particularly homogeneous mixtures? Heterogeneous mixtures are kind of like a picture here and a picture here and a picture here that are separated in space. So we can sort of take what we already know about pure substances and apply them to heterogeneous mixtures. It's the homogeneous picture where things get a little bit interesting, and this is where solutions come in. We'll touch on that in the next module. We didn't say anything about how particles in a substance interact with each other. We talked a little bit about chemical bonding, but can interactions happen across molecules? That's an open question, and that is a question that you'll address in your introductory chemistry course. And then the basic question of within a molecule, or even within an ionically bonded substance, why do the atoms or ions stick together? What is a chemical bond exactly? This is also a question that you'll explore in detail in your introductory chemistry course.